In this lecture, we'll go over a few more algorithms for the maximum subsequence sum problem. We'll then take a look at some operations that are common to data structures.
The third solution, which runs in O of n log n time, is a very complicated solution. So we're really not going to spend any time going over the details of how this algorithm works. But I will mention that this approach uses a concept that we haven't talked about before, which is called recursion. Now, the idea with recursion is that we have a method that calls itself. So each time that we call the method, what happens is we actually reduce the size of the problem by some amount. So imagine if you had a method and inside there had the same method call to that same method. So it seems like we just keep calling the same method over and over again. But every time we make the call, we're actually going to reduce the size of the problem by some amount. And if we keep calling this method and reduce the problem size, eventually the problem size becomes small enough such that the solution becomes trivial. So then once we have that trivial solution, well, we solve that problem and we take that solution and then we send it to the previous call. And then we would send that solution to the previous method call and then send that to the previous method call and so forth. And eventually we're going to get back to the first method call and we should have the solution from all of the other method calls. So we're just kind of keep calling methods until the problem becomes very trivial. We solve it, we go back to the previous problem size and solve it, back to the previous problem size and solve it, and go all the way back up to our original problem. So then we can use those solutions to solve the original problem. This algorithm also uses a problem-solving strategy that we call divide and conquer. So the idea with divide and conquer algorithms is that we split the problem into smaller and smaller subproblems. And in this particular algorithm, we use recursion to do that. So we'll use recursion to keep splitting the problems into smaller subproblems until the solution becomes trivial. So that was the idea behind recursion. So that's the dividing part of the divide and conquer strategy. So what's the conquer part? Well, what we do is we combine the solutions, and then there's some additional work that's involved, but we use that to solve a larger subproblem. Now, we're not going to really do a whole lot with recursion and divide and conquer algorithms right now, but later on in the course, we will go over some different types of algorithms that do involve splitting up the problems into smaller and smaller subproblems, and then we combine them. So we will see examples of divide and conquer algorithms later on. We'll now take a look at the fourth algorithm, and this is the linear time algorithm that takes O of n time. Here's the code for the algorithm. I wanted to show that first before actually explaining all the details and why this works. So notice that at the very beginning, we declare variables max and sum, which are initially 0. And notice that we have one for loop. So this is one of the reasons why this is a linear time algorithm compared to the n squared or n cubed algorithms. So with each iteration, we will increment our sum. So we would take the value of a particular element, add it to our sum, and check to see if it's larger than max. And if so, that the sum becomes the new max. The new part is this section right here, right there, where we check if the sum ever becomes negative. We just say that the sum is 0. And we're going to see why that works, but the basic answer is if our sum ever becomes negative, there's no way that a negative sum can ever be our maximum sum. So we do want to eliminate any possibilities of having negative sums. So as I just mentioned, if the sum of the subsequence ever becomes negative, we just say 0 because our maximum sum cannot be a negative number. And since we only have one for loop, this is clearly O of n time. But the question we have to ask is, why does this work? Why is this correct? So I'll try to explain the reason as best as I can. So we're going to let j represent the end of the current sequence. So remember, if we look at the code, we still have j in there. So remember, I represented the beginning of the current subsequence. And notice that I was not in the algorithm at all here. And that's because we don't need I. because we really don't need to know where the actual best subsequence is. We just need to know the sum of that subsequence. But since we don't need to know the exact subsequence, we don't need to know where it starts, we don't really need I at all. But we still need J to indicate the end of the subsequence. Let's just assume that we have I in the algorithm, and maybe we're trying to improve algorithm 2. So what we're trying to say is if AI is negative, there's no way it can be the start of the optimal subsequence, because we can always find a better subsequence if we start with AI plus 1 instead of AI. So in fact, any negative subsequence, not just a single element, but any negative subsequence cannot be the prefix or the starting point of the optimal subsequence. So what we're saying here is if we have some subsequence from AI to AJ, and if that subsequence is negative, we can't use that in the optimal subsequence. There's no point in counting that. So we can actually just move I over. Now, we don't need to actually move I over by one spot. We can actually move it over to J plus 1. Any of the elements between I and J are no good for us because the whole thing is negative. So we can just say start at J plus 1 and see if we can find the optimal subsequence from there. It's actually quite common that we have an algorithm where we can easily figure out what the running time is. But at the same time, it's difficult to see that the algorithm is correct. And that last example was one of those cases. Clearly, we can see that it's O of n time because we have a single for loop. But we had to explain a little bit as to why this algorithm actually works. In fact, all algorithms require what we call a proof of correctness. So here we're going to use logic and arguments to show that an algorithm is correct. There are several different proof techniques that would be used to show that an algorithm is correct. There are direct proofs, there are contradiction proofs, there are contrapositive proofs, proofs by induction, so forth. Now for this class, we're not going to worry about proving the correctness of algorithms. There'll be other classes that you'll take that involve proof techniques, such as in the discrete math class or in the algorithms course, but we won't worry about doing that here. We'll just show you the algorithm and say it's correct. Maybe we'll explain a couple things to show why it's correct, but we won't give a formal proof of correctness.